Hello everyone. Today we are going to see about viscoelasticity. It is very important property to understand and design a medical implants. Viscoelasticity materials that exhibit both viscous and elastic property when it is under deformation. It is very important to know about the viscoelasticity because many biological tissues like cartilage, tendon, ligament, skin, blood vessels are naturally viscoelasticity. When we design our implants, they should have similar mechanical properties like the natural one to the surrounding tissues. Otherwise, it can cause the stress concentrations or tissue damage or even pain. So, viscoelasticity is more important to design an uh, implant material. Then, elastic property. It is the ability of the material to bounce back its original position when the stress is removed. We can represent it as spring, and when we apply the stress, the strain is increases. When we remove the stress, the material can back to its original position. This is elastic property. It is the reversible deformation and it follows the Hooke's law. Here the stress is elastic modulus into strain. And then viscous property. It is different and it is the property of a material that resists the flow or deformation under an applied shear stress. We can represent the dashboard to explain the viscosity. Here the shear stress is proportional to the rate of strain. Here the neta is viscosity coefficient. And then to understand the viscoelasticity model mathematically, the James Clerk Maxwell uh, derived one Maxwell model in 1867. Here, the spring and dashboard connected in series so that the stress is same. We can find the total strain, the sum of strain from the spring and the dashboard. It is better for the stress relaxation. It describes the stress relaxation very well. And then the governing equation. First one is spring stress. Here stress is elastic modulus into strain. We need only strain rate, so we can rewrite like this and we differentiate with respect to t so that final equation comes like that. And dashboard stress is stress equal to viscosity coefficient into strain rate. We need only strain rate, so we can rearrange the equation. To add the strain rates, we add the two strain rates. This is the final and fundamental consecutive formula for the Maxwell model. And another one is stress relaxation. When we apply the constant strain to the material, the internal stress is decreases gradually over the time. When when we apply the strain, first the stress is not decreases, but when we the stress is continue for a long period of time, the stress is reduced. Here we can assume the strain rate is 0. The expression shows the exponential decay of the stress, and tau is the time taken for the stress reduces over the time. The stress relaxation is important to know and design the implant material. And another important property is creep. When we apply a constant stress to the material, the strain is gradually decreases over the time. Here, the epsilon naught of t here, rate of strain. Here, it shows the instant elastic strain from the spring. Here, there is immediate creation of strain from the spring, and the second one is linear viscous strain. It is from dashboard. It is a gradual decrease in strain over time. To add this, we can get the creep. This is the final graph and the equation of the Maxwell model. When the spring and dashboard connected in series, the stress is same but the strain is different, so we add the strain, and this is the final equation. This model is very useful to understand the viscoelasticity materials very well. Thank you.